Every year, billions of devices, from smartphones and electric cars to satellites and fighter jets, rely on materials most people have never heard of. Hidden inside every magnet, screen, and motor lies a group of 17 elements known as rare earths, the invisible foundation of modern technology. These metals are mined from rock deep beneath the Earth's surface, processed through complex chemical refineries, and transformed into microscopic fragments that power the digital age. They make our world faster, cleaner, and smarter. Yet their extraction and supply remain among the most challenging operations on the planet. So how do these ordinary-looking rocks become the critical materials driving our future? This is how billions of rare earth fragments build our world, from start to finish. Across China, Australia, and the United States, massive open-pit mines dig deep into layers of clay and rock containing rare earth minerals. Each year, more than 300,000 tons of these valuable ores are extracted, a process that begins with heavy drilling and controlled blasting to loosen the deposits. Gigantic haul trucks transport the broken rock to crushing stations, where machines grind it into smaller fragments for easier processing. Magnetic separators and flotation tanks isolate rare earth oxides from other materials like quartz and iron. At this stage, the ore contains only a few percent of usable metal, but it represents the foundation of nearly every advanced device on Earth. Before leaving the mine, samples are analyzed for purity and composition, ensuring each batch meets the exact chemical standards for industrial refining. Every ton of rock carries potential, the unseen beginnings of the magnets, screens, and batteries that define the modern world. The transformation of rare earth minerals begins deep within the industrial complexes built around the mined ore. Once the raw rocks are transported from open pits, they enter the first mechanical stage, crushing and grinding. Here, enormous jaw crushers and ball mills reduce massive stones into fine powder, allowing the valuable minerals to be separated from ordinary rock. The process is loud, constant, and driven by tons of rotating steel that pulverize thousands of tons every day. From this stage, the ore becomes manageable for chemical refinement. Next comes magnetic separation, where machines use powerful magnetic drums to pull out materials that react to magnetism. Many rare earth elements share magnetic properties, making this an efficient first filter. The remaining non-magnetic materials are discarded as waste or reprocessed to recover traces of usable minerals. What remains moves through conveyors to chemical treatment facilities, where the ore's metallic potential begins to surface. Inside the refinery, acid leaching becomes the key step. Crushed ore is soaked in concentrated acids, often sulfuric or hydrochloric, to dissolve the rare earth elements from the surrounding material. The resulting liquid, known as a leachate, contains valuable metals in ionic form. Every stage must be controlled carefully. Temperature, pH, and acid concentration determine the purity and yield. Large settling tanks then separate solids from liquid, creating a concentrated solution ready for extraction. From there, solvent extraction begins, a precise chemical balancing act. The leachate passes through multiple mixers and settlers, where organic solvents selectively bind to specific elements. Engineers adjust flow rates and chemical ratios to isolate each rare earth metal. It's a repetitive cycle. Mix, separate, and repeat hundreds of times to achieve separation of up to 99.9% purity. This stage defines the material's quality and determines its suitability for advanced technologies like magnets, batteries, and microchips. Finally, precipitation and drying turn the purified solution into solid rare earth oxides. Precipitating agents trigger the metals to fall out of the liquid, forming fine, powdery crystals. These powders are filtered, washed, and heated in industrial dryers, removing every trace of moisture. The result is a set of fine white or gray powders, chemically pure rare earth oxides, ready for conversion into metals. What began as unremarkable rock now carries the essential elements that drive modern industry. From here, the process transitions toward metallic transformation, where chemistry gives way to metallurgy. Once the rare earth oxides are purified, they enter the most critical stage of transformation, conversion into functional metals. Inside massive industrial furnaces, these oxides are mixed with reducing agents such as calcium or iron to strip away remaining oxygen, leaving behind metallic rare earths. This metallothermic reduction takes place under controlled heat exceeding 1,000 degrees Celsius, where precision determines both purity and yield. The result is solid metallic fragments ready for alloying. Each rare earth element behaves differently during reduction. Neodymium, dysprosium, and praseodymium are particularly valuable for their magnetic properties. These are combined with iron and boron to form neodymium iron-boron (NdFeB) alloys. Electric motors in vehicles, turbines, and countless digital devices, powering the foundation of modern motion and data storage. In specialized casting lines, molten alloys are poured into ingot molds and rapidly cooled. This rapid solidification controls crystal structure and ensures uniform strength across the material. Automated robotic arms handle each ingot with precision, moving them through a sequence of rolling, pressing, and slicing machines that reduce them into usable forms, thin sheets, rods, and magnetic blocks designed for specific industrial applications. After solidification, magnets undergo alignment and sintering. High-powered magnetic fields align microscopic particles, ensuring maximum strength and magnetic efficiency. Sintering then fuses the material at temperatures just below melting point, compacting it into dense, stable structures. Every step requires constant monitoring to maintain tolerance levels within fractions of a millimeter. The precision ensures performance consistency, a crucial factor for high-tech products like smartphones and satellites. Before shipment, these metal components are coated with protective layers to prevent oxidation and corrosion. Nickel, zinc, or epoxy coatings extend product life and preserve magnetic power. Final inspection teams use advanced scanning and flux testing systems to verify field strength, density, and dimensional accuracy. Only those that meet strict industrial standards move forward to assembly lines across the globe. Through this series of controlled transformations, the once inert ore has become the active core of modern innovation. Metal fragments capable of powering engines, guiding spacecraft, and storing data in the tiniest circuits. From the heat of reduction to the precision of alignment, this chapter marks the point where raw geology becomes the foundation of technology. Forged, tested, and ready to drive the world's most advanced machines. As refined rare earth metals leave the furnace and shaping lines, they enter the precision stage, where microscopic flaws determine global performance. Each fragment is now milled, cut, and prepared for integration into components used across electronics, energy systems, and advanced machinery. This is the finishing phase, where technology meets tolerance. Automated CNC machines polish every edge to an accuracy measured in microns. Magnets and alloys are ground down to meet strict dimensional specifications, ensuring perfect fit inside motor housings and circuit assemblies. In this stage, heat resistance, structural integrity, and magnetic consistency are measured against industry standards. Even a single deviation can cause device malfunction or energy loss. So every piece is tested repeatedly under simulated stress. Once ground and polished, rare earth magnets undergo magnetization, an exact process that gives them their field strength. High-voltage electrical currents realign internal magnetic domains, converting simple metal blocks into high-energy magnets. These are instantly measured using flux gauges to confirm polarity and power output. Only materials meeting full saturation are cleared for integration into manufacturing lines. The finishing floor operates with strict contamination control. Air filtration systems maintain purity levels comparable to semiconductor cleanrooms. Any dust or residual particles could weaken magnet strength or disrupt conductive pathways. Workers wear anti-static suits as robotic arms, transfer finished parts into sealed containers for storage and shipment. Efficiency and precision remain the top priorities. Parallel to magnet processing, other rare earth derivatives are transformed into phosphors and catalysts. Yttrium and europium compounds become the luminous coating inside LED displays, while cerium and lanthanum enhance catalytic converters in vehicles, helping reduce global emissions. These applications highlight how refined rare earths transition from raw material to essential elements of daily technology. Before global distribution, every finished batch passes through quality assurance labs equipped with X-ray diffraction systems and scanning electron microscopes. These tools verify internal composition, purity, and structural density. Final approval certificates are logged digitally, ensuring complete traceability from mine to market. This process upholds environmental and safety compliance for international trade. By the end of this stage, the journey from mined ore to functional component is nearly complete. What began as dust and rock now exists as precision-engineered materials driving communication, energy, and automation worldwide. Through rigorous testing, alignment, and inspection, each gram of rare earth matter proves its worth, forming the invisible framework of modern civilization. Once tested and certified, refined rare earth materials begin their global journey, transported from processing hubs to technology centers across Asia, Europe, and North America. Packed in sealed, anti-corrosive containers, these metals move through secure logistics chains that prioritize precision over speed. Every shipment is tracked by serial code, ensuring that each gram of neodymium, dysprosium, or terbium reaches its intended manufacturer without loss or contamination. The journey of these materials is as controlled as their creation. At international ports, tons of rare earth oxides and alloys are unloaded, inspected, and distributed to specialized factories. In China and Japan, most of the world's permanent magnets are produced, powering motors for electric vehicles, wind turbines, and robotics. The demand continues to rise sharply, with electric transportation alone consuming more than half of annual neodymium magnet output. From this point forward, the materials are no longer just industrial commodities. They become the silent enablers of modern technology. Inside motor assembly plants, precision-milled rare earth magnets are installed into rotors and generators. Each piece must align perfectly to produce efficient magnetic fields, converting electrical energy into motion. These same materials are also integrated into hard drives, smartphones, and advanced defense systems, powering sensors, stabilizers, and communication networks. Every time a car accelerates silently or a drone adjusts its position mid-air, rare earth elements are working in the background, unseen but essential. In the renewable energy sector, the impact is just as significant. Rare earth metals make possible the lightweight, high-efficiency turbines that turn wind into electricity. Offshore wind farms rely on large-scale generators that use thousands of magnets forged from neodymium and praseodymium. These turbines convert natural kinetic energy into clean power, a process that connects mining operations in remote regions to global climate goals. The circular economy of technology depends heavily on these hidden materials. As devices reach the end of their lifespan, recycling networks attempt to recover rare earths through advanced separation technologies. However, less than 5% of rare earth materials are currently recycled, making resource sustainability a growing concern. Researchers are now developing magnetic and hydrometallurgical methods to reclaim metals without chemical waste. Closing this loop will be critical to maintaining supply stability in the decades ahead. From the mine to the motherboard, rare earths move through an unbroken chain of engineering, logistics, and innovation. Their journey defines progress across industries, transforming dust into data, rock into power, and minerals into the invisible foundation of modern civilization. From rugged mountains to precision laboratories, rare earth materials undergo one of the most demanding industrial transformations on the planet. Each fragment mined, crushed, refined, and forged plays a vital role in powering the devices, vehicles, and machines that define the modern era. They are the hidden backbone of innovation, the silent force driving communication, energy, and defense systems worldwide. Behind every magnet, microchip, and motor lies a supply chain of extreme precision and global coordination. Every stage, from ore extraction to final integration, is a demonstration of human ingenuity and industrial evolution. The story of rare earths is not just about metals. It's about the pursuit of technological dominance and sustainability in an increasingly resource-dependent world. As demand grows, the future of these materials depends on responsible mining, efficient recycling, and innovation in alternative solutions. The challenge is clear: to maintain progress without exhausting the resources that make it possible. Humanity stands at the intersection of advancement and accountability, and the balance we strike today will shape the technology of tomorrow. If this journey amazed you, share, like, and subscribe. And don't forget the bell, so you never miss how the world is made, from start to finish. Up next, how the world's strongest anchor chains are forged, from steel to sea.